Section 8.3 is on page 474, talks about trigonometric integrals. And here in this section, we need a quick refresher of two main identities, the double angles. To start with, double angle, we know that the sine of 2 theta equals twice the sine of theta cosine of theta. It would help a lot if you are to solve for this, dividing both sides by 2. And every time you see a sine of theta times cosine of theta, it will save you a bit of time to use the sine of 2 theta, save you a u sub. Also, the cosine of 2 theta is the cosine squared of theta minus sine squared of theta. If you replace this by 1 minus the sine, if you replace this by 1 minus the sine squared of theta, you get this identity. And if you replace the sine squared with 1 minus cosine squared, you will get this identity. Now, it turns out we really don't need this one. This is just to show you where those two come from, really. So we need to know this for sure. I cluttered those, I always do, I apologize. So it seems we need to know this identity for sure. This one we really don't need. No need to worry much about it. But if I am to take this second equation, call this equation 2, and call this equation 3. If I take equation 2 and solve for cosine, that's what I will get. If you move the 1 over to the other side and divide by a 2, and if you take equation 3 and solve for sine squared, swap this with that and divide by the 2, that's what you'll get. Alright, so those are a must. And of course, the Pythagorean identities we must know. The sine squared plus cosine squared equal 1. If you divide by sine squared each of those, so sine squared over sine squared is 1, cosine squared over sine squared is cotangent, and 1 over sine squared is cosecant. If you go back to this equation and divide everything by cosine squared, sine squared over cosine squared is tan squared, cosine squared over cosine squared is 1, and 1 over cosine squared is secant, and that's how you could derive those identities anytime you need. So those are going to help a lot. And this section really deals with two types of problems. The product of sines and cosine powers and product, the product and the powers of secant and tangent. The rules apply to cosecant and cotangent identically almost. So I'm looking at page 479 in our book, and like we agreed, to really make this accessible to everybody, I have to type those in, so I altered the problem slightly. If you look at number 4 in the book, it looks very close to this, but it's a bit different. But it's the same idea. So when I glance at this, we really break it down to two types of problems with sine and cosine. When I glance at those, do I see an odd power of sine or cosine? If I see an odd power, then that problem doesn't require much. I always save the odd power term to be the du, meaning here, if I look at this, this is, I'm thinking out loud, this is going to be my du. If du is a cosine, can you guess what u is going to be? Well, with sine and cosine, that's simple. If I am to let u equal the sine of 3x, du will be the cosine of 3x times 3. So if I come back and do my substitutions, this right here is this right here. Well, it's almost there, except, there we go. I could replace that by a du, and the 1/3 I drag up front. And my u was actually that sign, but it's raised to the 6th power. Anytime I see an odd multiple of sine or cosine, this is the process. I save one of those to the power of 1, and that will be my du every time. And isn't this simply 1/3? Don't you add 1 to the power, divide by that? So wouldn't you say this would be 1 over 18 times whatever u was And what was, I'm sorry, u to the 6, I'm getting excited there. Add 1 to the power, divide by that. That's 21, and that is a 7. So what was u? Again, u was the sine of 3x. Now, if you have time, you can take a derivative of this. You should get that. So if I take a derivative of this, 1 over 21 is a constant. Bring the power down, subtract 1 from the power, times the derivative of the inside. Cosine of 3x times with the chain rule at 3. So altogether, 21 cancel with 21, and I'm left with sine squared, and there it is. What do you know? So you could do that if you have time, of course. If not, just hope for the best, and it's not a problem. Next problem up is number 14. So I want to say, well, okay, if it's odd, there's a rule. But if it's even, then you have to use power reduction. And in case you missed it, those are the power reductions. There's no other way of doing the problem. Any even power of sine or cosine, the only way to do it is to apply this as many times as it takes. So if I look at this problem, well, there's only one way of doing this problem. You're going to say this is 1 plus the cosine of twice x divided by 2 dx. That is 1/2. That's an x. And here, that would be the sine of 2x. If I take a derivative, I multiply by 2. When I integrate, undo multiplication, you divide. And there it is. That would be my final answer. So without an odd multiple of sine or cosine, you must use power reduction. Get the next problem. And number 18 prime. So the 3 is really not part of this problem, but when I'm looking at this, I have two options. I could either think of this as the sine squared of 5x squared, or I could think of it as the sine squared of 5x times this, and of course there's no difference between those. So most students prefer this, whatever works. If you do that, that would be sine squared of 5x, which is 1 minus the cosine of double the angle, 10x divided by 2. And this other cosine, this other sine squared would be the same thing, which is basically this. And now, this will be 3 over 4, the integral. And if I FOIL this, that's 1 minus twice the cosine squared of 10, twice the cosine of 10x, plus the cosine squared of 10x dx. And we run into the same problem. This is 3/4 the integral. This is 1 minus twice the cosine of 10x. And if you remember in trig, when you had to use power reduction on this, you always had to do it twice. There's only one way of doing this problem. You must use the power reduction on this. This here angle would be 1 plus the cosine of double that angle. Double 10x is 20x divided by 2. I know students don't like this, but there's no way around it. There are very few problems in this class in which there's only one way of doing them, and this is one of them. That's 3/4 times, and let's see how this works. This is simply x. This is the sine of 10x divided by 10. I'm going to take a 1/2 out of this. That's going to be an x, and that's going to be the sine of 20x divided by 20. And I'm going to call it plus c and call it a day. And that's pretty much it. So again, a bit messy. Not hard, just you got to remember this trick. Okay, so the general rule is, and this is the rule that you need to know. The rule for sine and cosine you need to memorize. The rule for secant and tangent I provide on the exam. So here, if the power of cosine is odd, you save a cosine factor. It's really simple. And if the power of sine, if you see those multiplied, you save a sine factor. And this is normally your du. Just think of that. So what do you take a derivative of to get cosine as sine and vice versa? If both powers are even of those trig functions, sine and cosine, then you must use power reduction, and in case you missed it, these are the power reduction. There's no way around it. So we dealt with the even power. Let's go for the odds. Let's deal with problem number 6. Let's look at problem number 6. I noticed that this is an odd power of cosine, so the way it works, I save a cosine of 3x. Remember, this is going to be my du. Every time you save a factor, that's your du. Wouldn't this be the cosine to the fourth of 3x? Well, what do I take a derivative to get cosine? I take a derivative of, so if I write this as cosine squared, right? And I'm writing all the steps so there's no misunderstanding or confusion anywhere. And now, to get a un, and this is my du, if I want this to be my du, then I know what the drill is. I know that I have to rewrite this as a bit more. I have to rewrite this as one minus the sine squared of 3x. And that's the trick. So if I do that, now let's observe what happened. If I let u equal the sine of 3x, then my du will be 3 the cosine of 3x dx. Well, I got it. This is really right there. Off by a 3, that's an easy price to pay. So there's my du. And this is simply 1 minus, and if I notice how this works, that's u squared. And that's how it always works. And wouldn't this be 1/3? And if you FOIL this, wouldn't that be 1 minus twice u squared plus u to the 4th du? Wouldn't you say that that would be 1/3 times u minus 2u cubed over 3 plus u to the 5th over 5 plus c? And if I go back and substitute what u equals, which is the yellow portion, that will be the sine of 3x minus 2/3 the sine cubed of 3x plus 1/5 the sine to the 5th of 3x plus c. That would be my final answer, and there it is. So if I see odd multiples of sine or cosine, that's the way it always works. Let me do another problem. And if I look at number 8, the same deal applies. I look at this. Once I see an odd power, that's good news, which means I'm going to save a sine of whatever that is. Again, this is going to be my du. That leaves me with sine squared of x over 4. And since this is going to be my du, what do you let u equal to get the sine and cosine? I have to write the sine squared as 1 minus the cosine squared, the Pythagorean identities that we talked about in the beginning, times the sine of x over 4 dx, and the usual. If I let u equal the cosine of x over 4, you know what, I could put that up there. Then my du will be negative 1/4 the sine of x over 4 dx, and a small price to pay if I let u equal this, right? Then du should be this. Well, there it is. I see it. Off by a constant, that's a small price to pay. There we go. So this would be a negative 4, the integral with a du. That's simply my sine x over 4 times dx, and 1 minus u squared. And it's a very simple integral from there on because, you know, this is power function, u minus u cubed over 3. So that would be a negative 4 into u was the cosine of x over 4 minus the cosine cubed of x over 4 over 3 plus c. That would be my final answer. On a test, I suggest you leave it like that. Don't waste time simplifying. For the back of the book, you should really match the answer identically on every problem. And that's how it should work. So, anything that's boxed, I accept on a test. And what if you have a combination of those two? Actually, it doesn't really matter. It turns out to be almost the same thing. Looking at problem number 22 times, suppose I want to do the following. Well, again, once I see there's an odd, I know what to do. I'm going to save a factor of sine of x dx. That's my du. Which means I'm going to rewrite, this is already in the cosine, but do you see that this would be the sine squared, and I have to write the sine squared as 1 minus the cosine squared of x. Hopefully I didn't lose anybody there. And I know how this works. If I let u equal the cosine of x, du will be negative the sine of x dx. Well, a simple price to pay. So if I follow my tradition, this is my u. This is really the integral of 1 minus u squared u to the 4th. And du is right there, off by a constant. So if I really replace it, it would be a negative du. Now, something you should definitely start practicing, that is converting the limits on the integral. That's a good idea. If I take 0 and I plug it in, again, since this is in terms of x, you want to plug for x, cosine of 0 is 1. And if I take pi over 2 and I throw that in, that will be to 0. That would allow you to finish the problem right there and not come back and substitute u back. That saves you a lot of work in this class. This is going to be, so this is really u to the 4th minus u to the 6th if you distribute that in, right? So that's going to be u to the 5th over 5 minus u to the 7 over 7, evaluated from 1 to 0. Of course, you could reverse the limits and switch the positive to a negative. I'm not going to worry about that. So if I put a 0, I'll get a 0. Minus, if I put a 1, I'll get 1/5 minus 1/7. Keep in mind, on a test, there's nothing wrong with this answer. For the back of the book, you should really simplify and you'll get a negative. And let me see, that will be 7 minus 5. 7 minus 5 is 2 over 35. So anything that's boxed on the exam is allowed. And I want to tackle a couple of more problems that are, you know, not matching either or. Let me get number 24 is the first of those. If you look at that, that's a bit hard to play around. You could multiply by the conjugate. That takes a long time. Again, that works though. Worst case scenario. But don't I know from before, didn't I know that the sine squared of x is 1 minus the cosine of 2x divided by 2? So what do you suppose this equal? If you cross multiply, wouldn't this be twice the sine squared of x dx? If you remember those identities, that would save you a lot of time. That would be radical to the integral. And wouldn't that be the sine of x dx? Now, I should throw an absolute value, but it seems, you know, majority of the problems in this book we kind of overlooked that. And what do you take a derivative of to get sine? Isn't that negative cosine of x plus c? So this would be negative radical to the cosine of x plus c. So those are kind of like mixed role in there, but they're still sine and cosine. And I have one more. And the last problem for this session so I'm breaking this into two sessions for you, is number 26 or 26 prime. I glance at this, again I could multiply with a conjugate that will take me a few steps, but if I recognize that this is the cosine squared of x dx, again this should be the absolute value. Assume that x is in quadrant 1. The book ignores that, so I'm going to ignore it, otherwise that will always come up. And wouldn't this be the sine of x plus c? And that pretty much concludes this section, this lesson. And in the next lesson, I'll go over the second half. Let me give you the homework. And there's your homework for this section, for this portion of the section.